Alright, let's begin where we left off. Okay, I'm going to kind of go speedy. So pause it, rewind it as needed, and we'll see if we can get through this. So this next item, the fundamental theorem of arithmetic claims that every natural number greater than 1 has a unique prime factorization. Does this mean that every natural number greater than 1 can also be created by summing prime numbers? And the answer is yes. So for example, let's explain why. This next bullet helps with that. Just demonstrate the difference of using prime factors versus prime add-ins by attempting to create the number 20. Okay, if we create the number 20 from only using primes, we can do a 2 multiplied by a 2, that is 4 multiplied by a 5, that's going to give us 20. And kind of if we work backwards, if we do the prime factorization of 20, if I divide that by 2, that's going to be 2 and 10. 2 is prime, 10. I'm going to divide that by 2. And these right here are my 3 prime factors that are used to create a 20. So if we use a different approach, if we use prime add-ins, so if I want to create a 20, I know I can do a 2 plus a 2 plus a 2 plus a 2. I can keep doing this 10 times, and that will give me a 20. Or I can not even use any 2's at all. I can just use a 5 plus a 5 plus a 5 plus a 5, and that will also give me a 20. I can use a 13, which is prime, and a 7, which is prime, and that will give me a 20. I can use a 17, which is prime, and a 3, which is prime, and that will give me a 20. So the answer is yes. I can create every natural number greater than 1 by adding prime numbers, because if I can do it by multiplying prime numbers, multiplication is kind of repeated addition, so I must be able to do it using addition. But the difference is this idea of uniqueness. So if I am using prime factors, so multiplication, there's only one way. This is the only one way in the universe to create the number 20. But if I'm using prime add-ins, there are several ways, and there's more than one. So the big idea is uniqueness, and this word unique is probably the most important aspect of the fundamental theorem of arithmetic. It is because of its uniqueness that we can use it to make the RSA encryption work. So internet security. Okay, your divisibility test. So the divisibility test by 3 claims that to check if a number is divisible by 3 with no remainders, that's an important idea, you simply sum each of the number's digits, and if that sum is divisible by 3, then the number must also be divisible by 3. For example, let's look at the number 42,762. The divisibility trick says add 4 plus 2 plus 7 plus 6 plus 2, and those sum to 21. And since 21 is divisible by 3 with no remainders, then 42,762 must also be divisible by 3 with no remainders. And then a cool fact, I think this came out of Vista. You can take the sum 21 and sum its digits, 2 plus 1, and keep going until you get back to the number 3. And if you get back to the number 3, then you got a green light. But if you get back to a different number, another number other than 3, then it must not be divisible by 3. So justify this divisibility test. Okay, 42,761, was that it? No, 762. Alright, so in our number system, ones, we've got tens, we've got 100s, we've got thousands, and so on, 10,000s. And I am going to see if a number is divisible by 3. First, I'm going to test each of these placeholders. So I'm going to take 1 and I'm going to divide it by 3. And I'm only going to observe the remainders. So there's going to be one remainder. Now I'm going to move over. 10, I'm going to divide 10 by 3. And I'm going to only observe the remainder. I'm going to divide, because your divisibility tests have everything to do with remainders. If we want to see if it divides with no remainders, we're going to only focus on the remainders. So 3 times 3 is 9. Okay, and after doing it a couple times, I hopefully will observe a pattern and come up with a conjecture. So my conjecture is going to be that it will continue this way as I continue to divide each of these placeholders by 3. Okie dokie. So, should be 1,000, not 10,000. Okay. So I'm going to convince myself that if I keep going on, no matter how far I go, there will always be one remainder in each of these placeholders. So I am now going to take this conjecture, this idea, I'm going to take my number, 42,000, and I'm going to expand it. I'm going to say that's 4 of the 10,000s plus 2 of the 1,000s plus 7 of the hundreds plus 6 of the tens plus 2 of the ones. And now I'm going to see if I can tally up how many remainders there will be. And so for every 1, there's 1 remainder. And if I have 2 ones, that means there's going to be 2 remainders. For every 10, there's 1 remainder. If I have 6 tens, that means there's going to be 6 remainders. And the same for hundreds. If I have 7 hundreds, that means I'm going to have 1 remainder for every 100. So I'm going to have 7 remainders, 2 remainders, 4 remainders. Now, I'm going to total up all my remainders. So 4 remainders plus 2 remainders plus 7 remainders plus 6 plus 2 gave us our 21. And I'm going to suggest that 21 remainders is the same as no remainders at all. So an idea similar to this. So 12 is the same as 3 multiplied by 4 plus a 0. 12 is also the same as 3 multiplied by 3 plus 3. 12 is the same as 3 multiplied by 2 plus 6. 12 is the same as 3 multiplied by 1 plus 9, or I can go the opposite direction. 12 is the same as 3 times 5 plus a negative 3. And so I'm kind of suggesting that these guys would be the remainders. And the 0 remainders is the same as 3 remainders, or is the same as 6 remainders, or 9, or 21, or 27. Okay, now let's create our own divisibility test with the number 4. So let's start off with the same approach. So let's take 1, let's divide it by 4. And there will be 1 remainder. 10 divided by 4, 2. So there's going to be 2 remainders. 100 divided by 4 is going to be 25 with no remainders. And now at this moment I can stop because I'm looking for the very first instance where it goes in with no remainders, because if it goes in with no remainders, it will go in with no remainders every time to the left of 100. So we'll go in evenly to 1,000, evenly to 10,000, evenly to 100,000. So just to prove it, we're going to have, let's do one more to satisfy our wondering. And there we go. So it will go in to 100 evenly with no remainders. That means there is no need to test the thousands, the 10,000, because if it goes into 100, 1,000 is just 10 100s. So if it goes into 100, it will certainly go into 2 100s, or 3 100s, or 4 100s, or 10 100s, and so on. So now, if we take that same number, 42,762, and let's test it for 4. So I'm going to have 4 of the 10,000s, plus 2 of the 1,000s, plus 7 of the 100s, plus 6 of the 10s, plus 2 of the 1s, and now I know that for every 10,000 there's no remainders, and if I have 4 of the 10,000 there will still be 0 remainders. Same for 1,000, 0 remainders. Same for 100, 0 remainders. So no matter the size of this number, the only digits that concern me are my 10s and my 1s. And I know for every 1 there was 1 remainder, so if I've got 2 1s, there's going to be 2 remainders. And 4 is not as fascinating as 3, because 3 was the same amount of remainders every single time. But 4, the remainders changed, so there was 1 remainder on the 1s, but then on the 10s there was 2 remainders, so that's kind of a pain to remember. So for every 10 there's 2 remainders. If I have 6 of them, that means there's going to be 12 remainders. So if I total all my remainders, 14 remainders, is that the same as no remainders at all? And the answer is no, it's not. If it were 16 remainders or 12 remainders, then it would be divisible by 4. So I'm going to suggest this number is not divisible by 4. And my divisibility test is simply this. I'm not going to worry about this nonsense of looking at the remainders. My divisibility test is just going to be check the last 2 digits, and if they are divisible by 4, then the entire number is divisible by 4. And we could say this: the number must be even. So for example, if this was 63, I wouldn't even test the last 2 numbers. I would just recognize that it's odd and say 4 cannot be a factor of an odd number, and so dismiss it quickly by the fact that it's odd. But if it is even, 62, and I don't have my times tables memorized all the way up to 62, so I can quickly just do 62 divide 4, and that's going to go in once. 22, 4 is not going to go into 22. It's going to go into 20, so there's going to be a remainder of 2. So since 4 does not go into 62 evenly, I know that there's no way for it to go into 42,762 evenly. So here's my rule: if it's even, then check the last 2 digits. If they're divisible by 4, then the number is. Okay, prove that 8 is even. Now, here's where we left off. Our definition of an even number is, it's got to be any natural that can be expressed as the sum of two equal, so those are both important, two equal natural addends. So this is where we are right now. We're going to expand this definition to include the wholes and the integers, but for right now and on this exam, we'll just leave off with our definition being anchored to the naturals, and we will re-anchor it later. So our definition's anchored to the naturals, and it has to look like this. It's got to be two equal naturals. So it must look like this. N plus n. This is right here. This is it, where n is a natural number. If we can make it fit this model, then that is the definition of an even number. So prove that 8 is even. Okay, 8, I'm going to see if I can have 8 manipulatives in my hand, 8 chips, and I'm going to see if I can maybe create two equal groups. So we'll go counter here, counter here, counter here, counter here, counter here, here, and we are done. So here's a group, and here's a group. I can only have two groups, and each group must be equal in size. So this group is a 4, this group is a 4, 8 is even. And if this is our definition of even, our definition of odd is just simply the same, two equal groups, but there's always going to be one left over. So this is odd, one left over. So prove that 9 is odd. Let's start divvying it up. Group, a group, a chip here, a chip here, a chip here, a chip here. So that counts for 8 chips. So I got two equal groups, and then there's one chip left over. 9. So it fits my model, so it's got to be odd. Now, let's prove that 8 plus 6 is even. Okay, I'm going to do kind of the same thing I'm going to do with manipulatives. So 8 and 6, here's the only thing I would suggest. 8 and 6 are kind of adjectives, and they're describing 8 ones plus 6 ones is even. So if I use manipulatives, 8 and 6 are describing the same thing. So I would suggest that we use the same manipulative. So for example, if I were to do this, 8 circles and 6, if I were to do 6 stars, then I have a little bit of a problem with that, because it's kind of implying that circles are different than stars. So we have two different items that we're talking about, but really we don't. We have one item. 8 is how many ones you've got, and 6 is how many ones you've got. And since they're both describing the same item, I think we should use the same manipulative. So I'm going to break 8. I just have shown that 8 is even. I kind of divided it into two equal groups. And now 6, I'm going to divide it into two equal groups. So I'm going to arrange my groups horizontally, and here I arranged them vertically. So however you want, but if I arrange them horizontally, so 3 ones on top, 3 ones on bottom. Okay, now look what I can do. I need to have two equal groups. If I have two equal groups, then I am in business. So I'm going to group this top row, and I'm going to group this bottom row, and then I'm going to say it must be even, because I have 1, 2, 3, 4, 5, 6, 7. So I have 7 ones in the top group, and I have 7 ones in the bottom group, and 7 ones plus 7 ones is my definition of an even. 2 equal natural number quantities. So it must be even. Prove that 8 plus 7 is odd. Okay, so here's the best way to go about your proofs. You've got to anchor this proof to the definition of an odd. That's probably the most important. We have to show the audience that here's my definition of odd. Odd is 2 equal groups of natural addends plus 1 left over. And if I can show that it fits this, by definition it has to be odd. So 8, let's do one more way with the manipulatives, then we're going to switch over to the arithmetic process. So 8, I'm going to divide it up into a group of 4 chips on top, a group of 4 counters on bottom. So 8 is even because it's 2 equal groups. 7, I'm going to go 3 on top and 3 on bottom, so that's 6 plus 1 left over. Now, I'm going to, so this is move number 1. Move number 1. Move number 2. I am going to see if I can make it fit my definition. So move number 2, I'm going to group my top and I'm going to group my bottom into 2 equal groups. So that's step number 2. Step number 3 is there are 7 in the top group plus 7 in the bottom group plus 1 left over, and that equals n plus 1. So number 4, it is odd because it fits the definition of an odd, which is n plus a 1. So this is a pretty complete proof, kind of 4 steps. Step number 1, I'm going to break 8 into 2 equal groups using counters. I'm going to break 7 into 2 equal groups and counters, but there's 1 left over. Step number 2, I'm going to group my top, my bottom. There's 7 in each group. Then there's 1 left over, and voila, that fits my definition of an odd. So it must be odd because it fits the definition of the odd. So this is kind of a perfect little proof. Hard to dispute that proof. It's organized step by step, easy to follow, easy to read, easy to convince an audience. Okay, let's do it arithmetically. 7 plus 3. Let's prove 7 plus 3 is odd. Okay, step number 1. 7 is the same thing as 3 plus 3 plus 1. So that's kind of, I broke it up into manipulatives. Step number 2. 3 plus 3 plus 1 is the same thing as 2 groups of 3 plus 1. Step number 3. 3 is a group of 1 plus a group of 1 plus a group of 1. Step number 4. 1 plus 1 plus 1 is the same as 2 groups of 1 plus 1. Number 5. Alright, so that must imply that 7 plus 3 is the same thing as, I'm going to replace this with 7. 2 groups of 3 plus 1 plus 2 groups of 1 plus 1 6, and I think it was someone in George Washington that kind of suggested we could argue each of these steps. We can justify each of these moves, and that is where we are heading. As soon as we're going to anchor each of these steps to one of the properties of arithmetic, so like commutative property, associative property, distributive property, but we have not yet introduced those. So all you really need to do is anchor your justification to the definition of even or odd, and then we will introduce these other properties as we go, which allows us to manipulate chips and regroup things arithmetically. So that is where we are headed. But for now, all you need to do is worry about anchoring your proof to the definition of odd or an even, and we'll be in good shape. Okay. So now 6, let's say 2 groups of 3 plus 1 plus 2 groups of 1 plus 1 is equal to 2 groups of 3 plus 2 groups of 1. Okay, now these two ones right here I'm going to combine together, and I'm going to call those 2 groups of 1. Okay, I need to write smaller. So my 7th move, I'm going to say that my 2 groups of 3 plus my 2 groups of 1 plus my 2 groups of 1. So my definition is this: I got a group plus an equal group, and that's the same as 2 ends. So I've got it written like this right now: 2 groups of 3, 2 groups of 1, 2 groups of 1. And I'm going to rewrite that as 2 groups of 3 plus 1 plus 1. So I'm going to say that that is going to be my 8th move. 2 groups of 3 plus 1 plus 1 is the same thing as 2 groups of 5. And now I can stop, because I'm going to have 2 groups of 5 and 2 groups of 5. So number 9, my 9th step, it is even. So now I'm going to anchor it to my definition, because 2 groups of 5 fits my definition of 2 groups of equal natural numbers. So I am done. So either arithmetically or manipulatively, whichever approach speaks to you is fine. Let's look at, what one did we just do? 7 plus 3. So let's look at this guy. Let's prove that 6 plus 4 plus 8 is even. Okay, let's do maybe one more arithmetically. We've done a handful already manipulatively. So 6, step number 1. 6 equals 3 plus 3. And I'm going to maybe save some steps, which equals 2 groups of 3. So number 2, 4 equals 2 plus a 2, which equals 2 groups of 2. My 3rd move, 8 is equal to 4 plus a 4, which equals 2 groups of 4. So number 4, let's see, 6 plus 4 plus 8 is got to equal this plus this plus this. 2 groups of 3 plus 2 groups of 2 plus 2 groups of 4. And then next, 2 groups of 3 plus 2 groups of 2 plus 2 groups of 4 has got to equal 2 groups of 3 plus 2 plus 4. 6. 2 groups of 3 plus 2 plus 4 has to equal 2 groups of 9. So I'm done. 7. It is even because 2 groups of 9 fits my definition of an even, which is 2 groups of n. So as long as I can make it fit my definition, it has to be even, and it does. 2 groups of natural numbers. Okay. Now let's look at some of these proofs accepted by kids and determine if they're acceptable or not. Prove 5 plus 7 is an even number. I have circled groups of equal addends, so the answer must be even, because the definition of an even number is any number that has groups of equal addends. So they kind of have circled, that's a group of 2, that's a group of 2, that's a group of 2, group of 3, group of 3. But we're going to dismiss this because the definition of a natural or even number, kind of understand the concept, but they're missing the big picture. This does have groups, but we want only one group plus one group. We want 2 groups, and each of those 2 groups have got to be the same size. So right here they have circled 5 groups. So they've got 5 groups of equal size. Well, they're not all 5 the same size, because this has 3 in it and this has 2 in it. But they've got 5 groups, and they are not all of equal size, so we got some problems. So 2 problems: too many groups, and some groups are larger than others. So we need 2 groups, but they've got to be the exact same size. So let's look at this next one. Okay, 4 plus 6 is even. So 4 is 2 groups of 2, 6 is 2 groups of 3, so the answer must be even, because the definition of an even number is any number that has 2 groups. So now the definition is getting a little better. 2 groups, they told us how many groups of equal addends. Okay, this is very close. So all they have proven here, they have only proven that 4 is even and that 6 is even. 4 is even because it has 2 groups of 2, and 6 is even because it has 2 equal groups of 3. So if they want to show that 4 plus 6 is even, they must do this. They must go one step further, and they must tell me here is a group, one group, and here is one group. So now I've got 2 groups, and each of the 2 groups is equal in size. They each have 5 ones in them. So this is not acceptable, but with a little work it could be. Okay, what about this guy? Now we're looking better. So when I'm looking for even, I'm looking for 2 groups. So prove that 5 plus 7 is even. Alright, so they've got, let's see what we've got. 5 is shown as 5 stars. 7 is shown as 7 stars. The top group has 6 stars in it. 1, 2, 3, 4, 5, 6. The bottom group also has 6 stars in it. The sum of these 2 groups must be even, because the definition of an even number is any number that has 2 groups of equal addends. Okay, that's perfect. That is perfect. The only thing maybe that would make it even better, of equal, you gotta tell me, it's picky, but it's got to be anchored to naturals. But that's awesome. That's very good. Okay, and kind of an arithmetic approach. 5 plus 7 is an even number. 5 is the same as 2 groups of 2 plus 1. 7 is the same as 2 groups of 3 plus 1. This implies that 5 plus 7 is the same as 2 groups of 2 plus 1 plus 2 groups of 3 plus 1. 2 groups of 2 plus 1 plus 2 groups of 3 plus 1 is the same as 2 groups of 2 plus 2 groups of 3 plus 2 groups of 1. So they kind of combine these ones together. Alright, number 5. 2 groups of 2 plus 2 groups of 3 plus 2 groups of 1 is the same as 2 groups of 2 plus 3 plus 1. 2 groups of 2 plus 3 plus 1 is the same as 2 groups of 6. So 5 plus 7 is an even number. I love it. But let's anchor this to our definition, and that will make it flawless. Because, kind of like this one before, how this one was because the definition, they anchored it to the definition, and that makes it hard to dispute. Because the definition of an even is 2 equal groups of natural numbers. So n plus n. So it's kind of 2n, and what we have is 2. So ours looks exactly like theirs. We have 2 groups of natural numbers, 2 groups of 6. Okay, now let's see if we can pick these apart. These are submitted by 6th graders. Determine if we find them unacceptable or acceptable. If we find them unacceptable, find a counterexample. So number 1, an even number is any number that can be expressed as the sum of 2 equal add-ins. So now hopefully we got some clever kids, and we'll say, well, what about this? What if I have 5.5 plus 5.5? That equals 11. So definition of even numbers is just got to have 2 equal add-ins. So 11 is even, because it has 2 equal groups. 5.5, 5.5. And we'll dismiss it. We'll call them clever for proving that 11 is even. But we got to dismiss it because the add-ins must be natural. Okay, any even number is a number that can be divisible by 2. Okay, and this is kind of in the same boat. I can argue that 11 can be divided by 2. 11 can be divided by 2, and the result is 5.5. Any number can be divided by 2. So look at this bottom one. Be divided by 2 with no remainder. So therefore this top one, 11, must be even. So this one kind of has 2 problems. So let's look at the bottom one. The bottom one will illustrate the second problem. An even number is any number, so that's loose. That's including a lot of numbers that can be divided by 2 with no remainder. What about this number? What about the number 8.4? I can divide that by 2. Let's see. No, I'm gonna put 4 there. 4 there. 4 times 2 is 8. I'm gonna put a 2 there. So 8.4, I can divide 8.4 by 2 with no remainder. So does that mean 8.4 is even? So we got to be specific about what setting up the parameters of these. So here we go. I'm going to dismiss all 3 of these. This bottom one. If I were to put this word right here after any, is any natural number. And then the top one, an even number, is any, we got to put it here too, natural number that can be divided by 2 with no remainder. So we got to put with no remainder. Okay. So the big idea, proof. What role does definition It plays a huge role and important. We always want to anchor our proofs to definition. And if you can do, whoops, I'm not sure, my spelling's not very good. If you can anchor it to definition, then your evidence is undisputable. You will be an excellent lawyer, and that is the entire strategy, is to compose a compelling argument. So this idea of logic plays huge into strategy of defending arguments. So cool trivia, Euclid, Greek mathematician who very well have written the most famous, successful, and influential probably is my key word, text ever. So he composed a book that is our geometry is based off of today, and a lot of our logic. So his book is second only to the Bible in the number of editions published. His book, The Elements, consists of 13 books containing definitions and proofs. Abraham Lincoln was very fond of Euclid's Elements. Elements played a fundamental role in his study of law. So Lincoln carried a copy of this and just pored over it and studied it, and it helped him understand the skills in developing a tight argument. And so it's kind of an idea of logic, composing arguments and anchoring your arguments. I mean, you want to prove them, you want to anchor them to solid definitions. Okay. That's it. We did the GCF and LCM. So I think that is it. We're done. So that's your review. Good luck in your preparations. Feel free to contact me if you come up with a question. And good luck.